The catastrophic explosion of a star is referred to as a supernova. The explosion of a thermonuclear supernova, in particular, indicates that a white dwarf star has been obliterated entirely, leaving nothing in its place. At the very least, this is what the theories and observations of astrophysics suggested. Therefore, it came as a complete surprise to the group of astronomers who used the Hubble Space Telescope to investigate the site of the unusual thermonuclear supernova, SN 2012Z, that the star had survived the explosion. Not only had it survived, but after the supernova, the star was actually shining brighter than it ever had before. In this video, we will discuss about that mysterious star. But before we start our video, please subscribe to our YouTube channel and also press the bell icon for all the latest updates. So let's start. These findings were presented at a press conference during the 240th meeting of the American Astronomical Society by the first author, Curtis McCulley, who is also a postdoctoral researcher at the University of California, Santa Barbara, and Las Cumbres Observatory. The findings were also published in an article in the Astrophysical Journal. These perplexing findings shed light on the background of some of the most prevalent yet inexplicable explosions that occur throughout the cosmos. These thermonuclear supernovae, sometimes referred to as Type 1a supernovae, are among of the most essential instruments in the toolkits that astronomers use for calculating the distances between cosmic objects. Observations of these explosions beginning in 1998 revealed that the expansion of the cosmos has been occurring at an ever-accelerating rate since that time. It is believed that this is the result of dark energy, the discovery of which earned the 2011 Nobel Prize in Physics. Image of galaxy NGC 1309 in color taken before the supernova in 2012Z beginning in the upper right-hand corner, clockwise, the location of the supernova prior to its explosion, SN 2012Z during the visit in 2013. The contrast between images taken prior to the explosion and those taken in 2016. The location of SN 2012Z, according to the most recent observations made in 2016, McCulley et al. Deserve credit for this. The scientific community has only a limited understanding of where thermonuclear supernovae come from, despite the fact that these events are of critical significance to the field of astronomy. Astronomers are in agreement that they are the result of the annihilation of white dwarf stars, which are stars that have a mass comparable to that of the Sun, but are only about the size of the Earth. Nobody knows what causes the stars to blow themselves up. A companion star may provide the white dwarf with some of the material that it needs to survive. As the white dwarf continues to accumulate more mass, thermonuclear reactions in its core will eventually ignite, which will result in a runaway explosion that will destroy the star. The strange form of thermonuclear explosion that occurred in SN 2012Z is frequently referred to as a Type 1a X supernova. They are the cousins of the more typical Type 1a. However, they are much less powerful and bright. Some researchers have hypothesized that these explosions represent failed attempts at producing Type 1a supernovae because to their lower power levels and longer durations. The most recent observations provide credence to this theory. The neighboring spiral galaxy NGC 1309 was observed in great detail and captured in several photographs taken by Hubble in the years leading up to the discovery of the supernova 2012Z in 2012. This galaxy had been observed for many years before 2012Z. In 2013, photos were captured by the Hubble Space Telescope as part of a concerted attempt to determine which star in previously captured images related to the star that had exploded. The analysis of these data in 2014 proved fruitful for the scientific community. They were able to determine the identity of the star that was located at the precise location of the supernova 2012Z. The progenitor star of a white dwarf supernova was found for the very first time at this point in time. When we got the most recent data from Hubble, we were expecting to see either of two things, McCulley said. We were expecting to see either of two things. Either the star would have entirely disappeared, or maybe it would still have been there, which would imply that the star we saw in the photographs taken before the explosion wasn't the one that exploded. Nobody was anticipating the discovery of a surviving star that was even more brilliant. That presented quite the conundrum. Macaulay and the rest of the crew believe that the reason the star that had only partially exploded became brighter was because it expanded to a much larger state. The force of the supernova was not sufficient to clear away all of the material, and as a result, some of it has returned to form what is known as a bound remnant. They anticipate that the star will, over the course of time, gradually revert to its initial state, with the exception that it will become larger and less massive. In a strange twist of logic, white dwarf stars have a greater diameter proportional to the smaller amount of mass they possess. Andy Howell, an adjunct professor at the University of California, Santa Barbara, and senior staff scientist at the Las Cumbres Observatory, remarked that the survival of this star is comparable to the fictional character Obi-Wan's return to the Star Wars universe as a Force ghost. The forces of nature attempted to bring down this star, yet it managed to come back stronger than any of us could have dreamed. Even if it appears to be in a new form, the star in question is the same one. It was beyond the reach of death. For many years, astronomers were under the impression that Type 1a supernovae occur when a white dwarf star's mass increases to a particular threshold, known as the Chandra limit, which is around 1.4 times that of the Sun. Because many supernovae have been discovered to have a mass that is lower than this, and because new theoretical concepts have shown that there are other things driving them to burst, this model has partially fallen out of favor in recent years. This is because of both of these factors. It was unclear to astronomers whether or not stars ever came close to the Chandrasekhar limit before bursting. The authors of the investigation have come to the conclusion that the growth of SN 2012Z reached the maximum possible limit and then stopped. According to Macaulay, the findings have profound ramifications for Type 1a supernovae. We have discovered that supernovae are capable of reaching their maximum size before exploding. Despite this, the explosions are not very powerful, at least not always. Now, we need to figure out what causes a supernova to fizzle out and become a Type 1ax, as well as what factors contribute to the formation of a successful Type 1a supernova. That is what we have for today. Leave a comment down below with your thoughts and reactions to the video. Tell us what you think. Don't forget to subscribe to our YouTube channel and click the bell icon so that you don't miss any videos. See you in the next video. Thanks for watching.